Hi, my name is Rodrigo Aldana, and today I will be presenting our work Distributed Differentiation with Noisy Measurements for Exact Dynamic Consensus. Let's start by answering the question, what is a distributed differentiator? So, in the differentiation problem, you have a scalar signal of interest, then you have a noisy measurement for it. Moreover, we assume that there exists a constant L, which bounds a high-order derivative of the signal of interest. And the goal is to estimate the first m derivatives of set of t. A differentiator is an algorithm that is able to achieve this goal. And for practicality, we require this differentiator to have the following features. We require our differentiator to be causal, which means that you only use past and current information at time t. You also require it to be exact, which means that you obtain the derivatives exactly in the absence of noise. We also want it to be robust, which essentially means that under noise, the estimations stay close to the true derivatives. The differentiator proposed by Levant has precisely these properties. It is causal, robust, and exact. It takes the measurement signal and injects it to this algorithm, which has n+1 outputs. Each output is in charge of estimating a particular derivative of the signal of interest. And if the noise stay bounded, the following error neighborhoods are reached after a finite time. In the distributed setting, you have n agents, which can communicate according to a network modeled with an undirected graph. We assign a weight to each agent, wi, which might mean, for example, the confidence or the quality we have for that particular agent. And finally, for each agent, we have a measurement signal. This might be a noisy measurement of the same signal for all agents, or might be a noisy measurement of different signals of interest distributed across the network. Our goal is twofold. First, we want to reach dynamic consensus towards this time-varying signal, which is essentially a convex combination of the local signals of interest weighted by the local weights. We also want to estimate the first m derivatives of this consensus signal. This can be very useful in a sensor fusion setting, where each of the agents measure the same variable of interest across the network, with perhaps different levels of noise. It is typically the case in which the noise signal is normally distributed with zero mean and variance given by sigma squared. A popular fusion rule is computing the following weighted average, where the weights are the inverse of the local variance, giving more importance to sensors with higher quality measurements. Moreover, it is often the case that this variable of interest is the output of a higher order state-space dynamics. Hence, computing higher order derivatives of the output might enable estimation of the whole state depending on the observability properties of the system. Our solution to this problem is based on the concept of exact dynamic consensus. In our solution, each agent I at time t reads a measurement from its local sensor. It also has stored m+1 auxiliary variables. Each agent shares with its neighbors the difference between the measurement and the first auxiliary variable. And finally, it updates these auxiliary variables as follows. We propose the following dynamics for the auxiliary variables. Let me break down each piece of it. First, note that we weight the error contribution according to the local weight here. We also introduce the sign parameters which are assumed to be the same across the network. These yj's are the shared information from neighboring agents. And as a whole, these are consensus error correction terms, which will be zero once consensus is reached. Finally, we have a chain of integrators for the auxiliary variables, which will be useful to compute derivatives. As a first result that we obtain in our paper, we can ensure consensus in finite time without noise. In particular, the difference between the measurement signal and the first auxiliary variable converge to the weighted average as desired. Moreover, once consensus is reached, then these error correction terms vanish and we are left with a chain of integrators, which means that each auxiliary variable is a derivative of the next one. This motivates the definition of the following outputs, which will be the difference between derivatives of the local signals and the auxiliary variables. Hence, if we assume that we can measure these derivative signals as well, then we can ensure that these new outputs converge to the derivatives of the global average. We can extend this result when we have noise. In particular, if we assume that all noises have the same bound, we can also show that each one of these outputs are close to the true derivatives, and the error bound is very similar to that of the robust exact differentiator, which depends on the size of the noise. However, we cannot forget that in order to build these output signals, we have to assume perfect knowledge of the local derivatives. In practice, these are obtained through a local robust exact differentiator. Let's try to understand our solution so far using the following diagram. In the case when we have no noise, then the local signal enters both the exact dynamic consensus block on the top and a robust exact differentiator on the bottom. On the top, the exact dynamic consensus communicates with neighboring agents in the network. From there, we compute the auxiliary variables, which are then combined with the output of the robust exact differentiator in order to compute the derivative estimates as the difference between the output of the robust exact differentiator and the auxiliary variables from the consensus block. Now let's see what happens when we add the noisy signal instead. In this case, the performance of the robust exact differentiator deteriorates with noise, regardless of the cooperation with the rest of the agents. And the reason is that the robust exact differentiator has no feedback from the network. Note that we can remove the robust exact differentiator since it is not needed for consensus. However, without this block, we lose the capability of reading the estimates of the derivatives of the global average signal. This begs the question if we can get rid of the local differentiator without losing the global differentiation capability. Let me explain our solution for this problem. If we knew that at agent I the signal of interest is exactly 0, then the output would be the difference between just 0 and the auxiliary variable. This is, we compute the output as just the negative of the auxiliary variable without the need for an additional local differentiator. The problem is that this is no longer useful, since if the signal is exactly 0 and we know it, then this agent does not provide any more information to the network. Despite this, we can still leverage this idea to solve the problem of getting rid of the additional local differentiator. Recall that we have the original n agents. Each one of them is composed by its local weight and its local measurements. We propose to add n additional auxiliary virtual nodes, where we copy the same weights as the original agents, but the measurement signals are just set to 0. With this new configuration, the new average will be composed by the contribution from the original average and a contribution from the virtual nodes. In particular, on the top, there is no contribution since the measurement signals are just set to 0. And on the bottom, we have the copy from the original weights, which add up to twice the sum of the weights. This means that the new average is half of the original average, when we can just correct this simple scale factor multiplying by 2. Hence, once consensus is reached, the virtual nodes will have access to half of the original average signal and its derivatives without the need of a robust exact differentiator, since the local measurement signals were all set to 0. In order for these virtual agents to be useful, we need to modify the original topology, which can be assumed to be, for example, as follows. Then we connect each virtual node to its corresponding original node. In practice, each agent is in charge of 2 nodes, its original node and its new virtual node. The original node is the one that communicates with other agents. In contrast, the new virtual node is useful to read the derivative estimations without the need of an additional robust exact differentiator. In some sense, the new virtual node plays the role of a local differentiator, but it has the advantage of receiving direct feedback from the network. Therefore, our main result in this work is that with this configuration we can achieve robust exact differentiation of the global average signal in finite time with suitable error bounds in the presence of noise, and all this without the need of a local differentiator. Let me just explain a small nuance in these results, which I omitted up to this point for the sake of clarity, and is that consensus towards the signal of interest is reached only if the initial conditions comply with this condition, which is trivially satisfied if we set the initial conditions for the auxiliary variables to 0. This condition can be restrictive since it doesn't allow agents to connect or disconnect from the network. However, we can also account for this effect if we add these damping terms, which will get rid of the mismatch between the initial conditions asymptotically. In the following, I will show a small example in order to clarify the ideas presented so far. First, assume that you have a circular graph with 10 nodes. The weights for each node were assigned randomly. For the sake of simplicity, the local signals measured at each node are waves of different amplitudes, frequency, and phases. Finally, we generated the noise signals uniformly. The following simulation is what happens when there is no noise. As you can see, all agents are able to reach consensus towards the weighted average signal, marked in the dotted red line. Now, when we add a little bit of noise, you can see that the local estimations are able to stay close to the global derivative. Now let's draw some conclusions for this work. We were able to propose a new distributed differentiator, the first of its kind, capable of reaching consensus towards the weighted average of time-varying signals. Derivatives of this weighted average are able to be computed exactly without the presence of noise. Robustness guarantees are able to be obtained in the presence of noise, which have similar asymptotics as the standard robust exact differentiator. Moreover, the local signals are assumed to comply with assumptions standard in the differentiation literature. And finally, we remove the need for an additional local robust exact differentiator. And that's it. Thank you for your attention.